Hello everyone. Today I'm going to give a short presentation on our new result, a deterministic incremental all-pair shortest path data structure that has polylogarithmic, update time, and stretch. And this talk is based on joint work with Sebastian Forster and Yasamin Nazari. Okay, let me jump right in and set up the problem and the model. Good. So we are working on a problem on the all-pair shortest path problem. So statically, what that means, one way of phrasing it is that you're given a graph. On the right-hand side, I drew a graph that is unweighted, but generally we allow for weights. And now what you want is you want to compute a data structure, you want to compute it quickly, and then you want to be able to query for any pair S to T of vertices S to T for the distances in G. So here, for example, S and T have distance 1, right? One way to do it is to, for example, just run all pairs shortest path and then have a matrix where you store for every pair of vertices the distance explicitly. And here we are considering the incremental setting. So in this problem, the graph is not static, but instead it is undergoing edge insertions over time. And we want our data structure to essentially have the same operation. So we want the query again, but now we additionally want to allow for an insert operation. So we want to allow for inserting in a new edge and then the querying again. Now, unfortunately, it's quite difficult to achieve anything in this model if you don't give a little bit of slack. So what we'll allow for is actually an alpha approximation, where in this talk we'll consider alpha to be really close to 1, so 1 plus epsilon. So again, what we want in this talk is for a graph undergoing edge insertions, we want a data structure that is able to answer queries for any pair of vertices S to T up to an alpha approximation. And then we want to be able to insert new edges and do more queries and then more edge insertions and so on. Good. So we could have the graph on the right-hand side. S and T could be the first query pair, and then you would hopefully get something very close to 4 or even 4. And then what could happen is an edge insertion like this one, which changes the distances significantly. And now if you would query the pair S and T again, you would hopefully get a distance that estimate that is much closer to 1. Again, the query is really for arbitrary vertices S and T, so you might also query these two vertices afterwards, and then you would get hopefully something close to 3. Good. I hope the problem is clear. I'll say a little bit about the model. It's really important for this problem to distinguish adversary models for applications. So there's many algorithms that only work against oblivious adversaries. And nowadays we are trying to get really fast algorithms for adaptive adversaries. Oblivious adversary means that the update sequence is generated before, so all the insertions are generated before the algorithm is started. And you should think of it as just a list of edges being written down by the adversary before you even start the algorithm. And then what you do is you basically feed the first edge into the algorithm, and now you can ask it for different pairs, and then you feed the second edge, and you can again ask for multiple distance pairs and so on, and so on. And this is in contrast to the adaptive adversary, where the update sequence is generated on the go. So it's not initially that before the algorithm starts, but instead the adaptive adversary generates the first edge, it feeds it into the algorithm, and then it might query a lot, query for different distance pairs, and only then it will generate the second edge. And the huge difference is that now the second edge can be designed specifically to make it harder for the algorithm to function properly. But in applications, what we want is we want adaptive adversaries because many applications just require this adaptive adversary model. Good. One thing to point out here, because we will present a deterministic algorithm, deterministic algorithms work by default against adaptive adversaries, just because they are always designed against the worst case sequence, and that's exactly what an adaptive adversary is going for. Okay. Let me briefly summarize also the state of the art and then jump right into our contribution, and then I'll talk a little bit about the techniques. Before I'll do that, I'll also briefly mention the motivation. So I've already mentioned this a little bit, that we basically want this strong adaptive adversary model. The reason is that partially dynamic all pair shortest paths. So this means either insertions only or a different setting where you have the all pair shortest path problem, but with deletions only, which is called decremental. So for these two settings, the motivation is that there's many real-world graphs that actually are incremental or undergoing deletions, which is called decremental. These data structures that we then get for this partially dynamic setting can often be used as internal data structures in fully dynamic problems. We have static algorithms via the MWU multiplicative weights reductions that are very powerful and basically require this data structure that we talked about as an oracle to compute all kinds of graph problems. So you can derive an approximate max flow algorithm, multi-commodity flow algorithms, min-cost flow algorithms, all of them approximate. But you also see it as subroutines in many other algorithms to generate spanners, or also in the recent exact min-cost flow algorithm. And most of the time, we are actually looking a little bit more at the decremental setting. So the deletions only setting is more important for applications, but the incremental setting is nonetheless an important setting and is a really good test bed also to see what you're getting, because it's generally considered a little bit easier. Okay. And I mentioned this already. For all of these applications, you really need a strong adversary model, and getting data structures in the strong adversary model is normally much harder than getting it in the oblivious one. Okay. Now let me go to the state of the art, and here I'll just have very few selected results just because the literature is huge. So I have to select a little bit out of what we have. And there's first an amazing result from 2014, where basically you can get all pair shortest path with the approximation n to the little o of 1 with runtime almost near linear, so m to the 1 plus little o of 1. And this was a randomized algorithm that worked against oblivious adversaries. And then later in 2018, Zurich obtained an algorithm that generalizes this much more to different case, which is also a really interesting algorithm. Again, it works against an oblivious adversary, and these runtimes are really optimal up to a subpolynomial factor, so to the n to the little o of 1. And then more recently, there was work that obtained this result deterministically, so against adaptive adversary. And even the approximation was very recently improved by Schutzoi to a polylog in n. But the big open question, and all of these algorithms that we are seeing here, they essentially work in the decremental setting. But at least for the first one, it's very clear that it also works in the incremental setting. And I think for the other ones, they can be actually worked into incremental algorithms as well. But even in the weakest model, so oblivious adversary, and even if you take the incremental problem as an easier problem, what we didn't know so far is an algorithm that has an approximation of polylog n and a runtime of m polylog n. And that is exactly what we get in this paper. So this is really almost as good as it gets. The stretch approximation and the distance estimates could be a little bit better. But other than that, there's very little room to improve. And also our algorithm is already deterministic. The only downside is that this one is really incremental only, and there really isn't a way to make it decremental. At least we couldn't find one. But I think this already gives a strong indication that for the decremental setting, there should be an algorithm that probably achieves the same guarantees. Okay. Now let me talk about the techniques a little bit. So here, what we did is we looked at static distance oracles, a recent paper by Andoni, Stein, and Song, and they obtained static distance oracles. So already you in the static setting, you do all pairs paths, but you're already allowing for a stretch. And they designed a new algorithm for distance oracles that works very well in parallel. This is not what we'll concentrate on, but I'll mention, or I'll now give an overview over their approach, at least roughly, and then I'll show how to work it into an incremental algorithm, at least a little bit. The talk is rather short, so I'll keep it short and brief as well. Good. So initially, you can think of you're given this graph. Again, I'll use no weights just since it makes the presentation easier. And what you do is you sample a 1/b fraction of the vertices initially. And here b is a parameter that you can choose, so you're free to set your b. Good. So they suggest to sample this 1/b fraction, and then for each vertex, so for each of the gray vertices, you basically look at the sampled vertices, which we'll also call pivots, and you find the closest sampled vertex / pivot that you can find. And sometimes you have to break ties arbitrarily, so you can maybe see, if I'm using the mouse, you can see that this vertex really could have has distance 3 to this sampled vertex and distance 3 to this one. So it's not really clear which one he should choose, but you can just break ties arbitrarily. And then you get these clusters, which is basically drew which vertex has which pivot or is assigned to which sampled vertex. Okay. Then what you do is you basically want to project everything onto the sampled vertices in the cluster. So what does that mean? Now, you want to create another graph on a higher level. And now you want to, so the vertices of this new graph is just a sampled vertex set. So it's only supported on the sampled vertex set. Another perspective is just to have a contraction of each cluster into this the sampled vertex, but I actually prefer to just limit the support to the sampled vertex set. And then what you need to do is you need to think about a reasonable way to project the edges, or to also find edges on the supported vertex set. Because here in our example, there's no edges going directly between sampled vertices, so this would just be an empty graph if you don't take care of this issue. Okay, so there's two types of edges that Andoni, Stein, and Song propose that you should use in the next level graph that you're producing. So the first type is for every vertex, you look, so here I'm fixing a vertex u, you look at its ball, the open ball up to the to its pivot vertex. So it doesn't include the pivot vertex or any vertex at the same distance as the pivot vertex, but all the vertices that are closer, strictly closer. So for you, it's exactly the 5 vertices in this green ball. Now for each of these vertices in the ball, what you do is you insert an edge between the two cluster the pivots. So here we have U, and its pivot is the vertex over here, which we call PU, the pivot of U. And we have V, the vertex V, to be in the ball of U, and its pivot is this sampled vertex over here. So what you do, because of this relationship, you're going to add an edge between the pivot of U and the pivot of V, and you're using the distance from the pivot of U to U, the distance from U to V, and the distance from V to the pivot of V as the new edge weight. So this new graph that we are generating is going to be a weighted graph. This is the first type of edges, and these edges is what we call the ball edges, because we generate them using the balls of each vertex. Now I drew another vertex here, so in U's ball there's also V prime, right? You would also add an edge here. It's exactly the same edge, so you would create a multi-edge, but here the result would really be the same. Other vertices that you pick in the ball would now create a loop because they point to the same pivot. In larger examples, you get more interesting kinds of edges that are between pivots. Okay, so these are the ball edges, and then there's a second type, which we call the projected edges. So a projected edge is just for every edge that you already have in the initial graph G, so an edge, say, from X to Y, I drew it in blue. What you do is you project it up to the pivots of the endpoints. So between the pivot of X and the pivot of Y, you now create an edge just because these two have that relationship. And you can see that this blue edge would not be generated from a ball edge as a ball edge because X's ball is just the empty ball, or just a ball that contains X, because Y is as far as its pivot, and the same is true for Y. So there would not be a connection between the pivot of X and the pivot of Y if it wasn't for this projected edge. Okay, so both of these are really important. Now I'll do a little very high level analysis. So we're calling this new graph, this graph that we generated from the ball edges, the projected edges, and support on the sampled vertices. We call that an emulator graph. What we say is that it will have n over b vertices and n b log n edges roughly plus m edges. So m is the original number of edges in your graph. The proof is super straightforward. We sample the 1 over b fraction of the vertices, so therefore there have to be n over b vertices in the emulator. Then we analyze the ball edges. So how many ball edges did we generate? So each ball contains e log n vertices with high probability. This is a hitting set argument where you basically order all the vertices in by distance from a vertex. So you have a vertex U, you order all the vertices by distance from U, and then you know that with high probability, one of the first b log n or order b log n vertices is hit with high probability by a sampled vertex, and then only the vertices before the sampled vertex are included in the ball and generate a ball edge. So each vertex generates b log n ordered b log n ball edges, and that gives a total of nb log n ball edges. And then we have the projected edges, but here we just take every original edge in the graph and then we create one projected edge. So we must have exactly n projected edges. Okay. There's another lemma that's crucial. We'll not prove it, but this lemma says that for every 2 vertices that are in this emulator H, so in this new graph that we generated, what we have is that the distances are up to a constant factor, the same distances as in the original graph. So you're only losing a constant factor here. Good. Now that we have the setup, I'll not go too much into any of these proofs anymore, but just now that we have the setup, the natural thing is to do a hierarchy. So you generate an emulator of one graph. So you have H1 maybe initially, and then you generate a next level graph, and then you subsample that graph and you generate another emulator of that, and so on. So you have a hierarchy, H1, H2, H3, and so on of graphs, where you have less and less vertices because at each level you subsample the vertices you support, that you support on. Okay. Let's try to do just a rough analysis of everything. So it's crucial that you define your sampling parameter very careful to get a log n approximation in the end, because you have a constant approximation at each step. What you can allow for is only very few levels. So here what we do is we set the sampling probability, the b, so the 1 over the sampling probability, we set it to be doubly exponential. So here bi, so b at level I, we want to be 2 to the 6 over 5 to the power of I. And then you take the, and then we define b smaller than, less than equal I to just be the product of all of these b's that are smaller. We define ni to be n over b less than equal I. We define m1 to be m initially, and then mi recursively to be mi minus 1, and then plus an ni bi log n. All of these numbers will make a little more sense in a second. And then the fact is that you can get a certain k, which is log n. This makes sense because we are choosing like a doubly exponentially increasing function for bi to choose bi. So you get a k log n, where b less than equal k is larger than n, Okay. Using all of these numbers, what you get is the following lemma, which is a lemma about the hierarchy. So basically, let's define H1 as our input graph G equal to our input graph, and then just take HI plus 1 to be the emulator with the procedure we've seen of HI. We do that for each level up to a level K for this K of log n that satisfies what I've written in the fact. And in each level, we sample with this increasing parameter bi. Okay. And what we'll have is that the distances in H, I, and G are equal up to a constant to the I factor. And now since the largest level I is K, which is log n, we just get a log n approximation in HK to G, and of every HI to G. And what we have is that each HI has at most mi edges and ni vertices. It's a bit, you need a little bit of care, but basically the mi just comes from the initial m edges, and then you basically add at each step, you project the original edges. So this just keeps your mi to be the number of edges from the level below, so mi minus 1. And now you have to add the ball edges in. But if you choose the bi's like we do, then you can actually bound the number of ball edges to be very small, so of order polylog of order n polylog m. Good. So now we have this hierarchy that essentially says that we have at level K, we only have at most one vertex left, and at every level we have few edges. Good. This pretty much is all that you need to know about the hierarchy. And once you have this hierarchy, it's actually straightforward using rather standard techniques to query the right distances, using just going through the levels and looking for the pivots of vertices and looking in the graph. Good. Now I'll explain how to modify this construction in the incremental setting. So we suggest as an incremental algorithm first that basically when you maintain the balls and the pivots for each vertex u, what you do is you change your pivot only if its distance decreases by a 1 plus epsilon multiplicative factor, instead of maintaining it very naively where you would change the pivot whenever there's a sampled vertex that comes closer, because distances are now decreasing over time. So what does this mean? So for our example, right, we looked here at this ball of u and the generated ball edge as well to v. What could happen is that you could have an edge insertion from u to v, right? And now the second, so the sampled vertex, the pivot of v here also moves closer to u. But we'll not make it the pivot of u just because of that small decrease in distance, but instead this will not really change our distances and our edge rates at all, unless the edge really goes rather directly and the distance between u and the next pivot or some pivot or some sampled vertex that is not the pivot of u yet moves significantly closer to u, which then allows us to basically and then we would change the pivot of u to this vertex, which changes the clusters. But then we also know that the next ball of u has significantly smaller radii. Okay. And this incremental algorithm modification is rather standard, I'd say. So you see this in a lot of partially dynamic algorithms already on shortest path. And what you get is basically that all of this pretty much still works. The only problem is that because each vertex now changes its pivot and its ball roughly log n times, right? After every time you reduce the radii by a 1 plus epsilon multiplicative factor, so you will have, depending on the epsilon, you will you'll actually have log n times that you change the pivot. And this just means that you will have a blow up in the number of edges that you project that you have in the next level graph in the emulator and the runtime by roughly a log n at each level. Good. And the main challenge, so all of this would be rather simple, but then you actually hit a challenge, and this challenge or what makes it really difficult to obtain the result, the m polylog m update time and the polylog m stretch, is that this is not good enough, because if you're now doing edge projections and instead of projecting each edge once, you're projecting each edge log n times, then the first time you project, you're getting from m to m log n edges, or the m log n edges. And thus, if you're projecting naively, just the edge projections will, after k levels, mean that each edge from the original graph after k levels was projected up to log n to the k times. And even for k being log n, this will be a subpolynomial and not a logarithmic factor anymore. I have a small illustration. So let's say you have this edge here between the two clusters in H1. You would project it up between these two clusters. You would project it up between these two vertices in H3. So this is just like in the static case. For each edge that you have in H1, you would generate an edge in H2, and each edge in H2, you would generate an edge in H3. But then as soon as things are moving a little bit and clusters are changing, because of the same edge in H2, you would again add an edge to H3. So you would generate a blow up from the number of projections, because at each level you are projecting each edge now log n times. And the fix that, or the solution that we'll offer, that we offer in the article, is that you project more directly across multiple levels, which is very intricate to set up, and there's a lot of technical work that you need to get it right. A lot of careful technical details that you need to work out, and you need a couple of new edge types. So in the end, it's all not as simple as the original data structure, but I think it's still a fairly simple algorithm for given that we are in a partially dynamic setting. And in the end, all of this basically works out to give a nice m polylog m algorithm with polylog stretch. Okay, let me give a very brief conclusion. So what you've seen is the first algorithm in the partially dynamic setting, no matter which adversary model you use, that achieves m polylog m update time and polylog m approximation. Our algorithm is even deterministic, which means it works in the strongest model. And also quite interesting, even though we are the algorithm really builds on this framework of Stein, Andoni, and Song. This is a framework that looks very different from previous dynamic algorithms in that space. So we also think it's quite interesting in terms of new techniques that are brought into the setting. And finally, I'll close with the big open question: can we basically find a decremental algorithm with the same guarantees? Because that would really have a lot of very cool applications. Okay, this concludes the talk. Thank you very much for your attention.